California. My paper is about abstraction hierarchy and self-annotation update for fine-grained activities. So what is fine-grained activities? So this type of activity is more finer level than the standard activities. The datasets I'm using in this paper is called kitchen dataset. It contains 64 fine-grained activities like wash objects and wash hands, like cutting strips and cutting into dices. So the challenges for this problem is it has a very low inter-class variability. It is really hard for you to tell the difference between the wash objects and wash hand. And also, there are 12 actors reading this data, so therefore there is a multiple ways of cutting strips, which means it will have high intra-class variabilities. So in order to solve this problem, our motivation is to try to recognize by grouping and also decomposing them into a hierarchy multiple abstraction layers. In the right, this is our HAN representation. We have meta level layers, and also we have base level layers. We have infra level layers. For each video, we will generate a representation from meta level to infra level. So the HAN model contains 3 different layers. The first layer is the base level layers. It used the labels given from the datasets, and the meta level data is grouping by our algorithms, and the infra level is just by decomposing our base level nodes. So in our solution, we will try to find out what type of nodes should be grouped together. So our strategy is to find the most similar nodes in the total activities. Therefore, we propose a similarity matrix to grouping this activity. And about how to decomposing the activities, we will use a linear, unsupervised way to do the clustering. And then we are gonna compose a HAN structure, and then giving an input video, we are gonna giving a full output for the video representation. So this is an example for the meta level activity. For example, we can see we are gonna grouping the take food from the fridge and put in the oven into the same activities, and we are gonna group wash hands and wash objects within the same meta level nodes. And also we are gonna deposing the base level activities. For example, like here we can deposing cutting into dices into 2 different finer nodes, and then each of the finer nodes will have their own representations for the attributes. And this is a full representation from the coarse to fine. You can see, giving a video, we will generate a coarse level representation, like take and put in something into a home appliance. And also we will generate a sentence at the final level called person putting cucumbers using hands. And in our experiment, we show a 5% improvement compared to our baseline. And also we test our algorithm in the attribute prediction, which gave us 5% in action and around 2% to 1% in other attributes like container, tools, and ingredients. So this is about this paper, and another paper is talking about another problem, but also still related to activity recognition. It is called activity recognition and prediction with post-based discriminative patch model. So our goal is to explore how to using the post information into activity recognition problem. One of our motivation is coming from here. We can see if I only show you the left image, it is really hard for you to tell what activity it is. But if I show you the right pictures, it is easier for you to tell me this is playing golf. So my motivation is, I think we should using post patch instead of post configuration in the activity recognition problem. Another observation makes me thinking about this is because right now the post estimation algorithm is not that accurate. Therefore, the post configuration features generated from the post estimation results is not that accurate and discriminative enough. So therefore, our solution is to use post patch instead of post configuration. And also we are gonna building a tree structure to integrate all these discriminative patches. So here is a, a, a framework for our PDP model. First, we are gonna train the activities using an initial PDP model, and then we are gonna do a mining for the discriminative patches. By combining these two together, we can train a activity recognition model, for example, like for the pull-up, playing golf, and running. So, and then after applying this activity into the input frames or videos, we can see like this one got the highest confidence. Therefore, we will give the prediction as pulling up. So our algorithm containing three major parts. First, we are gonna using some algorithm we designed to mining the discriminative patches. Our two metric is first, we are gonna guarantee the purity within these activities, which means there are less intra-class variance, and also the interclass should be very discriminative. And we are using a very standard way for the tree structure part-based model and to inference what will be the confidence for this video with this activity. And we think about the patches as a latent variable, so we're using a latent variable machine learning framework, and then this is using the dual coordinate descent algorithm. So we test our algorithm into two different data set. One data set is called sub-JHMDB. It contains 12 activities and with around 600 videos in total. So in our experiment results, we approximate get 5% improvement compared to our baseline, and also like in these figures, it shows our improvement in each individual activities. And on the second, we test our algorithm on another still image activity dataset. It's containing 5 activities like running, walking, playing golf, and sitting, and so on. We also achieve some like 3% improvement on this dataset. So in this paper, our conclusion is like it is better to use post-patch instead of post-configuration when the post-estimation results is not accurate enough. So that's about my paper. Thank you.